All right, everyone, I'm going to be helping you out with Rolles theorem today, and I'll just get right to it. So obviously you can pause the video if you need to write this down, but just to take it one step at a time here, Rolles theorem is let f be continuous, so let a function be continuous on the closed interval from a to b. Okay, so think we have an interval there from one x value to another x value, and differentiable on the open interval. So also you can take the derivative between those two numbers. So think, it can't have any vertical asymptotes, can't have any cusps. That means it's differentiable. If the output at the beginning of the interval equals the output at the end of the interval, then there is at least one other number, c, so somewhere in that interval, such that the derivative at that point is equal to 0. Okay, so how does this make sense? Let's look at some pictures. Let's start with the picture on the left here. Okay, here's our interval, and again, this would be a good thing to sketch in your notes. We have a starting point at A, we have an ending point at B, and what they're saying is if this function is continuous on this interval, okay, on the closed interval, so including these 2 points, and differentiable, so there's no cusps, no vertical asymptotes, anything like that, no jumps, then there is at least one number, c, okay, so in this case right here, such that the derivative at c is 0. So what it's trying to tell you is, in a situation like this is kind of a basic example, your output at A is the same as your output at B. It must go down or it must go up at some point to get back to that, and at that point at C, at that maximum or minimum, you have a derivative that's 0, meaning you have your tangent line, the slope of your tangent line is 0, so your derivative is equal to 0. Okay, on the right is obviously just a situation where this would not work because it is continuous, right? If I'm tracing this function, I don't have to pick my pencil up. However, it is not differentiable. It has a cusp right here. We can't take the derivative at that point. So Rolles theorem would not apply for a situation such as this one on the right-hand side. Okay? All right, so let's use that information to work through a couple examples. Okay? So I'll do 3 examples with you, and one of these Rolles theorem is not going to be able to apply. Question is, does it apply? And actually, let's find that value if it does apply. What is my c value where my f prime of c is 0? So let's ask ourselves these questions. Is the function continuous over the closed interval from a to b? So from -5 to 3, is this function continuous? Well, right off the bat, I can see I'm not dividing by anything, so there's no vertical asymptotes here. It's not an absolute value function, so there's no cusp going on there. And actually, if you were to plug this into your graphing calculator, it would look something like this, just a sketch. Okay, obviously quadratic, so we got a parabola. Obviously, it's continuous between those 2 numbers. There's nothing going on there that doesn't make it continuous. Is it differentiable from those 2 points? Again, no vertical asymptotes, no cusps, no anything like that. So it is differentiable. And I'm just thinking back to number 1. If I said cusp, I didn't mean to say cusp. I should have just said vertical asymptote or jump. The cusp is more when we're dealing with derivatives. Okay, so that's number 2. So obviously we can take the derivative anywhere from -5 to 3. There's no, like I said, no jumps, no cusps, no vertical asymptotes. Are the endpoints the same? Okay, so that's the first thing that we have to check is our endpoints. So I would say f of -5 is equal to, now let's see what our output is. This would be -5 to the second plus 2 times -5. And when I do that, I get 15. Okay, so now we have to do one more check. Let's see if that works for our second endpoint. So it works for -5. Let's see if it works for 3. So this is going to be, instead of x squared plus 2x, I have 3 squared plus 2 times 3. Okay, that's 9 plus 6 is 15. All right, so we passes that test. Our endpoints have the same output. Okay, so that means yes, Rolles' theorem does apply. And let's go and find that value C. Let's find that value between these two numbers where my derivative is 0. So all you have to do next is just take the derivative of f of x. That's going to be 2x plus 2. Now we want to find where the derivative is equal to 0. So all we're doing now is just setting the derivative equal to 0 and solving. Okay, bring the 2 over, so 2x equals negative 2. When you divide out, you get x is equal to negative 1. So at x equals negative 1, we've got either a relative minimum or relative maximum on that graph, and actually that would make sense, right? It's kind of like picturing it just right here at negative 1. You can see where that derivative would be 0. Okay? All right, let's try another one. Next one is, again, does Rolles' theorem apply? If yes, where is the derivative equal to 0? Let's go through each question at a time. Now this is an absolute value graph. Absolute value of x minus 3, let's put 3 right here. It would look something like this. Okay, is it continuous? Yes, it is continuous. Okay, if I'm tracing this graph, I don't have to pick up my pencil. Is it differentiable? In fact, it is not differentiable because we have a cusp or a sharp edge right at 3. So this is a no. We have to be able to pass all three checkpoints in order to use Rolles' theorem. So this is going to be a no. Rolles' theorem does not apply. Now, I want to make sure we get these explanations right in case you see this in the future. We're going to say Rolles' theorem does not apply. And let's list our reason why it does not apply. Our reason is that the function f of x is not differentiable over the interval, and it's going to be the open interval from -1 to 7. Okay, so again, think of -1 over here, 7's way up here. So over that open interval, not including these endpoints, it has to be differentiable, and obviously at 3 it is not differentiable, so this right here would be our answer. Okay. All right, finally, one more. This is one that's going to have to require a little bit more work. At some point here, we're going to have to use, it looks like, if we do use Rolles' theorem, we're going to have to use the product rule to take the derivative, right? We're multiplying, consider that your first, consider that your second. Now, before we do that, let's check these checkpoints. Is it continuous over the closed interval from -1 to 3? Again, we're not dividing anything. We have no vertical asymptotes going on here. There's no jumps. So if I were to trace this graph, I wouldn't have to pick up my pencil. It is continuous. And actually, again, if you checked it in your graphing calculator, it would look something like this. Okay. So that's our first checkpoint. Is it differentiable? Can we take the derivative between these two numbers from -1 to 3? Again, there's no cusps, there's no jumps, there's no vertical asymptotes. So yes, we could take the derivative over this interval. There's no problem with that. Are our endpoints the same? So that's that third checkpoint we always have to do before we take the derivative. And so let's check our endpoints. Let's do f of -1. Okay, that's going to be -1 minus 3, parentheses, -1 plus 1, squared. Well, that's just going to be 0. That's going to zero out the whole thing. Let's try f of 3. Now that's going to be 3 minus 3. Again, that's going to zero out everything. 3 plus 1 squared. Again, that's going to be 0. So our endpoints are the same. Okay? So this is going to work. We can use Rolles' theorem. We just have to find a point between those two, between -1 and 3 on that open interval, where our derivative is 0, right? Where our tangent line has a flat slope, is a 0 slope. So I'm going to say f prime of x is equal to, now again, let's go back and remind ourselves of the product rule. This would be first derivative of the second plus second derivative of the first. Okay. So I'm going to go first. Derivative of the second. Now, derivative of the second, you're going to have to use the chain rule here, right? So this is going to be 2, copy paste the x plus 1, times the derivative of the inside. Well, the derivative of the inside is just 1. So this is going to be first derivative of the second plus second derivative of the first, so x plus 1 squared. Derivative of the first is just going to be 1. Okay, so second derivative of the first, if you're keeping track. And really, we just need to combine a few things here. So let's say this is x minus 3. This is going to be, so the 1 just, I mean, that's just 1. So I'm going to distribute the 2. So I've got 2x plus 2. Okay, now plus, again, the 1 is just 1. It just stays the same, keeps everything the same. But I know that I can expand this next part out to be x plus 1, x plus 1. The reason I'm expanding everything out like this is because, remember, our ultimate goal here is to find where our derivative is equal to 0. So I want to set all this equal to 0, and I want to solve for those x values. Okay, so now we're going to have to do some multiplication here. When I multiply this through, that's going to give me 2x squared minus 4x minus 6. When I multiply these two together, I'm going to get x squared plus 2x plus 1. Remember, we're setting this equal to 0. We want to find where that derivative is 0. And at this point, we're just combining and factoring here. So this is going to be, I'm going to combine my like terms. 2x squared plus x squared is 3x squared. Combine my x's to be negative 2x or minus 2x. And the negative 6 plus 1 is negative 5. And set that equal to 0. You could use your calculator here to find your zeros. You could also factor this by hand pretty easily. So I'm going to set up my 2 parentheses. Now remember, we want to start with something that multiplies to be 3x squared. So if I start with 3x and x, now if I multiply those two together, that's going to get me to 3x squared. Only thing we really have to do now is think of, okay, what comes next? We want to find factors of negative 5. Obviously, we're going to try 5 and 1. It's just a matter of, is it negative 5 positive 1, or is it negative 1 positive 5? So let's just guess and check here. Plus 1. So if I were to go here, I'd go 3x times x is 3x squared. This would be 3x minus 5x gets me back to 2x. And then negative 5 times positive 1 is negative 5, so this is going to work out. Okay? So we're going to have two answers here. 3x minus 5 equals 0, and x plus 1 equals 0, but we have to be careful here. Let's go all the way back up. We're looking between the interval from negative 1 to 3. So we want our answers to be in that open interval. Okay, again, I'm going to go back to this wording up here, open interval. So we don't want to include those points. So if I'm solving for x here, it's going to be 5/3. Okay, 5/3 is obviously between negative 1 and 3. So this is a good answer. Okay, this one is going to be x equals negative 1. Be careful again. Negative 1, let's check that. From negative 1 to 3, that's a closed interval, but these brackets mean closed interval, but it says on the open interval from where the derivative is equal to 0. So we're really looking, when we're finding the derivative, actually let me write it down here so we're not confused. We're looking on the open interval from negative 1 to 3. And that means that we can't include these endpoints. We can't include those numbers. It has to be between those numbers. So this is actually not a value that we can use. Okay, so I know that at 5/3, that is where my derivative is equal to 0 over this open interval. Okay?